Hello everybody. In this video tutorial I want to show you how we can find an IC50 value from some recorded data and of course very importantly also the 95% confidence interval for this IC50 for this measurement. So here are our data. So we have an inhibitor and we do several concentrations of this inhibitor which span a huge range of concentrations. And we measure certain readout, an intensity, or in whatever assay we use. And we do the experiment in triplicates. So we've got 3 different readouts. And the first thing is that we need to find out what is the IC50 for this inhibitor, the half maximum inhibitor concentration. And there are lots of different ways to do that. The easiest way is probably using an online tool. There's one really good one. The link to that is in the description of this video. So I just simply copy my set of data, copy, and then I go to this online tool, the IC50 calculator, and the guys at AIT BioQuest have done a really great job. So all you need to do is you just simply paste the data in here. So paste. So here are our data. Then it says process data. So here are the data and it looks all good. Yep. And now we just simply calculate the IC50. And what we find is a nice plot here. Now what it plots here is really, in a way, the logarithm of our observations. So this is a logarithmic scale. We need to be aware of that. This looks like a nice sigmoidal curve here. And the really great thing is it gives you the IC50 value. So let's just simply copy this value, because we need it later. It tells you which equation it used and how this actually how it calculated everything. So we've got our IC50 value, and that was really easy. And so here we've got the IC50 value. I just simply paste this value in here. So here we've got the value 5.63 times 10 to the minus 7, and the unit of course is molar. Now obviously we want to do also a little bit of calculations in terms of the confidence interval. How good is this measurement here actually? What is the uncertainty in this IC50 measurement? And it's very well advised if we actually convert our inhibitor concentrations here to a logarithmic scale, and we can do that very easily. So I just put in here log of the inhibitor concentration and transform the data, our inhibitor concentration, into the log inhibitor concentration. So we get something like that, and I just simply pull that down here, and here I've got my log of the inhibitor concentrations, and that is actually what we are going to use for the calculation for our uncertainty for the IC50, or rather the P or the log IC50. Okay, so in order to do that, we need to do a little bit of calculations. Why? Because there is an equation that we can use. This looks like a total monster of an equation, but it's actually not too bad because these are things that we can calculate quite easily. And I show you in the following what is what for this margin of error, because what we want to get at the end is something where we say we have our log of IC50 plus minus this margin of error, which is given in this equation here. So what have we got? T critical, this is a critical T value. So we need a T value because that defines our margin of error. SE is indicated by the standard error of our regression. And that is what we are doing. We're doing a nonlinear regression. M, this value here, is the gradient of the regression. Gradient of regression at the point that we want to evaluate, at, let's call it y, that we want to evaluate. N is the number of observations, number of, well, in a way, x values, let's call it x values. K is the number of replicates. Y is the evaluation point. Y bar is the mean of the readouts. And this SSXX, that is the sum of squares, of the x values. And this is nothing else but the log inhibitor. These are these values. So what we can do is, from the data that we had previously, we just simply calculate an average intensity here by just simply averaging these data points here. So we can do that here. Equals average. We just simply average these data points and draw this down. And here we get the average of the data points. So if we now go, what we can also do is we can just simply draw a curve here, and we use the inhibitor concentration, the log of the inhibitor concentration on the x-axis. So that's our x-axis, and all the other things on the y-axis. We do a scatter plot. And what we see here is, again, we see this nice sigmoidal curve here that we have also seen in the output of the program. So we can replicate that with our Excel. Some people put in here error bars or something like that. I would not necessarily do that because we've got only 3 data points here for our read intensity 1, 2, and 3. So you really should not do massive error bars. It is more honest in a way if you just simply show these data points as they are. And of course, they can be summarized by this average intensity. Okay, so far so good. So we have our IC50. We've calculated that, or the program did that. Now let's see how we can calculate this margin of error and what these different things actually represent. So here is a list of all the things that we need to do. So the IC50, what was that? That was this value here that we got from our program. The P log IC50, that would be the negative logarithm of our IC50 value. That's 6.25. Now the number of observations that we have, this is the number of measurements that we have, so we can easily do that, equals count. And we just simply count how many we have. We could have done that by hand. So it's 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, we've got 9 counts. We need to calculate the number of the degrees of freedom. And in this case, the degrees of freedom, because we have 2 parameters, it would be n minus 2. So that is fairly simple. So that's 9 minus 2. So that gives us 7. K is the number of replicates that we are looking at. And we've said we have got 1, 2, and 3 replicates. So we've got 3 replicates. With that, we can calculate our first number that we need. That's the critical t value. And we can calculate that with Excel equals t dot inf to t. That's a two-tailed t-test. And we want a probability. So it is 1 minus the confidence interval. So that's 1 minus 0.95. And we have 7 degrees of freedom. That is this one. And that gives us a t-value of 2.36. Okay, now we need to calculate the next one. It's the standard error of regression that we are going to calculate here. And luckily, Excel allows us to use a function in Excel. This function is called standard error of regression yx. So this is the standard error of regression. And it asks us for the known y values and the known x values. So for the known y values, we just simply use the average intensities. These are our y values, like this, comma, and the known x values, we are doing everything with the log of the inhibitor concentration. That's why I've grayed out the non-log version. So we do this one here, close the brackets, and we get a standard error of this 101. We don't actually need to calculate the mean of the x values. We could, but let's just simply quickly do that. But we don't really need it for our equation. So that's average and our x values are these numbers here. So negative 6.01. Now we need to calculate the sum of squares here. And luckily, again, Excel has a function for that. It is called def square. It's this function, and we need to use these numbers here. So that's our sum of squares of all the x values. We need to calculate now the mean of the y values equals average. And again, we calculate the average of our y values. That's this one here. We need to calculate the y value at which we want to evaluate it, and that is actually the halfway point between here and here, between 0 and the average here. So that is 993.3 divided by 2. So equals this value minus this value divided by 2. That gives the halfway point. That would be for our x value. That is where we find the IC50. And now the last bit, that's the gradient. And that's a little bit a tricky one, because what we are looking for is actually the gradient at the point where we want to evaluate. So that would be the gradient here at this point here. So how do we find this gradient at, let me just simply draw it here. How do we find this gradient at the point that we want to evaluate? That's the halfway point, that's about 500. So we could calculate the first derivative of it, but that is really a pain. However, we can say, right, within this range here, we assume that our line of best fit is actually something like that. That it is linear. We know that the curve is not linear. We know that the curve is sigmoidal in shape, like that. But we assume that within this range here, it is linear. So we can try and figure out what is the gradient between this data point and these data points. And the important thing is that the point where we want to evaluate it is covered by these two data points. So let's go back to our data. Let's say we had our data point at 497. So that would be, the data point would be between this here. So 400 and, what was it, 490, yeah, roughly 497. So here we want to evaluate. We want to evaluate the gradient between these two data points. Let's just quickly highlight these data points. So we want to find the gradient between this one and obviously this one here. So that gives, these are the two data points, and we want to find the gradient of that. And that's, again, Excel allows us to do that, equals, that's the slope function. So we've got the slope. It asks us for the known y values. So these are our known y values. And the known x values. So these are the x values here. And we get a gradient of negative 523. So what we now have is really, we've got everything that we need in order to calculate the margin of error. And we can do that now. So let's quickly do that. Just make sure that it is visible. So let's calculate. Equals. So our critical t value, we've calculated that. T critical times our standard error of for the regression divided by the gradient where we want to look at it, divided by m, times. So now we go into the square root. Square root of 1 over the number of counts of observation plus 1 over the number of replicates. That's this one, plus, and now we are in this part here, we calculate at the evaluation point y minus the mean of y squared divided by our sum of squares of x times the gradient squared. We need to make sure that we've got all the brackets closed. We need one more bracket closed. And we get our margin of error to negative 0.35. So that is the margin of error. So what we can do now is we can make a little overview table with a figure, a plot, and where we get all the data together. So here we've got our log of the inhibitor, and just for simplicity I've plotted the average of the intensities. And when we do that, we get this nice sigmoidal curve. We've calculated the IC50 and also the log IC50, this IC50 that was from our printout from this calculation. And we've just calculated the margin of error. So what we can do is we can now calculate the bounds for the log IC50. So all we need to do is really, we need to calculate the log IC50 minus the margin of error and the log IC50 plus the margin of error. So we get here the range for the log IC50. So that is the 95% confidence interval for the log of IC50. And let's see whether this makes sense at all. So we said our IC50 would be the halfway point. So let's go here. So that would be roughly around the 500 part. So we have this here. And I make the line a little bit stronger so that we can actually see it properly. So that's the halfway point, and we would then go down here. Is this parallel? Yes, it looks reasonably parallel. So we add a line down here. That would give us our IC50 value. And again, I make this a little bit stronger. So this one here would be our IC50, or rather the log of the IC50. Log IC50. And we see it's between -6 and -6.5. So that's this value here. And that tallies quite nicely with our calculations. And now the margin of error goes from basically -0.5, which is probably around here, to -6.55, which is probably somewhere here. So here this would be our confidence interval. That is the 95% confidence interval. For the log IC50. And if we want this to be expressed not as the log but as the IC50 confidence interval, then all we would need to do is we would need to take these numbers here, just 10 to the power of this number, and we get the confidence interval for the IC50. But usually it's quite a good approach to work with the log IC50, or as I outlined earlier, with the p-log IC50, which is just simply to avoid the negative numbers. The p-log IC50 just records these numbers as positive numbers. So our calculation, our confidence interval looks in line with what we actually see here, and hopefully this makes sense and it shows you how we can calculate a confidence interval for a log IC50. So thank you very much for watching, and I hope you enjoyed that.